Hello everyone, welcome back to Deterministic Optimization. Let's continue our discussion on cutting stock problem. So here we're going to discover a linear programming formulation for the cutting stock problem that we set up in the last lesson, and to understand the key feature of this formulation, meaning the large number of variables, as we'll see the formulation will give. So again, this is a cutting stock problem. A paper company produces large rolls of paper, and customers demand smaller width, smaller rolls of different number of rows for each types of demand. And the company needs to meet the demand, meaning to completely satisfy the demand exactly, and to minimize at the same time the total number of big rolls used to satisfy demand. Because demand comes in arbitrary width, so the company may not be able to exactly use up all the rows, big rows, each big row. Maybe there are some waste part that cannot be used. And there may be many different ways to cut a big row into smaller ones. So the most economic and most optimal way to cut these big rows to satisfy all this demand is a highly non-trivial question. So the key concept is pattern. As we see, patterns are feasible ways to cut a large row into smaller ones to satisfy demand. We have seen several different examples in the last lecture. Let's put the patterns together into a matrix. So one pattern is represented, as remember, as a column of, in this case, in this example, 3 elements, because we have 3 different types of demand. So a pattern is a column vector with the number of elements equal to the number of different types of demand. So this pattern number 1, is 400, meaning a big row is cut into 4 copies of smaller rows of width 25, 0 copies of other 2 types, because it used up everything here. And the second pattern is to cut one big row into 3 copies of smaller rows of width 25, and not cut anything for 35 and 45. So in other words, I'm throwing away 25 width, not use it. That's wasteful, but that's feasible. So I'm going to consider that pattern here too. And third pattern is even more wasteful. I'm only using 2 of it, 2 copies, only cutting 2 copies of width 25 and throw away the rest, and so on. So you see there are tons of ways to cut a pattern, and I'm just organizing it in certain ways. The specific order does not matter. I'm just organizing it in a matrix. So see, this matrix here, say we have n total number of ways to cut this one big row into smaller ones to satisfy its demand. As long as it's feasible, I'm going to include it here. And in general, a column, a pattern, is specified by 3 numbers, A1, A2, A3. And these numbers are integer numbers, positive integer, non-negative integer numbers. It can be 0, but cannot be negative. It has to be integer, right? I have to cut integer copy of each demand. Okay, so this is a very long matrix, but short. So what is the right-hand side here? I'm putting demand quantities, 150 copies of first demand, 200 of second, 300 of the third. And you can see that I'm setting this up to really write a constraint. So let's set up decision variables. What is decision variable? Well, the decision variable is the number of large rows cut in each pattern, I. So I'm going to denote that by xi. So xi is the number of large rows cut in pattern I. Remember, a pattern I means that's a way to cut a big row, one big row. So the question is how many big rows you're going to cut in a specific pattern. And you're going to aggregate them together to satisfy the total demand, right? So the number of variables here is equal to the number of patterns, which is big N here, which is a big number. So again, this is the matrix that we put together for the patterns. And the columns here corresponds to decision variables, right? x1 means I'm going to cut this pattern, x1 copies, x1 number of large rows in this pattern, x2 number of large rows in this pattern, and so on. So x2s, x3s, x1, these xi's need to be non-negative, okay, and should be integers. But more importantly, it cannot be negative. It has to be non-negative. And what about constraints? Well, the constraints is to meet the demand with equality here. We want to exactly meet demand. We do not want to over meet demand. So how do we meet demand? Well, the demand comes in rows, right? For example, the first row here all correspond to how many copies of the first type of demand is cut in each pattern. So for example, 4 copies of demand 1 is cut. Multiply with x1, the number of big rows cut in this pattern is the total number of demand type 1, number of copies for demand 1 cut in all the big rows of demand of pattern 1. And so on for pattern 2, pattern 3, and so on. So you see that this exactly is this row of this matrix multiply inner product with x1, x2, the unknowns, right? You can do this for each row, and this should equal to the right-hand side here. So that we see that this exactly gives us a system of linear equality constraints. A is this pattern matrix, B is the right-hand side, X is a column vector of the unknowns, variables, and X should be non-negative. All right, what is objective function? Well, the objective function is very simple. It's just minimize the total number of large rows. So it's minimize the sum of x1, x2 all the way to xn. So if we put it together, we have a so-called Gilmore-Gomery linear programming formulation for the cutting stock problem. This formulation was first figured out, proposed by Gilmore and Gomery in their famous paper. So the formulation is minimize the sum of xi's from I to 1 to n. And the special thing here is the coefficient of this linear function is 1, right, for all the variables. So that is very special, and we're going to use this special structure. And the constraints are demand satisfaction constraint, right? Ax equals b, meaning I'm aggregating all the big rows together to satisfy each type of demand. And the big rows should be non-negative. The number of big rows cut in each pattern should be non-negative. And it should also be integral. But here, for our lesson, we're going to ignore the integrality constraint, assuming x can take fractional value. And later, we'll explain how to actually get integer values. But now we're going to solve this linear program. It's also called linear programming relaxation of the integer program. And you'll see a lot of this later in the later course, part of this course. All right, so the key feature of this formulation is the number of variables. The number of ways to cut a large row is big, and that means the number of variables is also very big. And this actually is the first time in this course that we encounter a linear program that is so big to even write down the entire model. Think about n is 1,000,000. Then how do you even write down the entire linear programming matrix? That takes a tremendous amount of storage to do it. And it can very easily run out of just hard disk space, storage space in a computer. But we still want to solve this problem. So that's exactly what the challenge is. So let's summarize. We learned this so-called Gilmore-Gomery formulation of the cutting stock problem. It's a very interesting way to formulate this problem. And we've seen first time a large-scale optimization problem. A large scale means a large number of variables.